Hello. This video is the first one on numerical integration. It follows after the general introduction to integration. And here I'll be talking about some techniques we can use to work numerically to find approximate values for integrals. The word integration itself means something like arriving at a whole by building up from the parts. And that is the way we're going to approach numerical integration. We'll be dividing our problems up into tiny parts and adding those up to give us the bigger picture that we actually want. So, as our first example, suppose we have water flowing in a pipe. And as the water flows through the pipe, what we want is to calculate the total volume that flows through the pipe. You're probably being charged for that water from your municipality and by the volume that you use. But what you can measure is the rate at which you're using it. So you'd like to go from the rate to the total volume to know whether you're being charged the right amount for your water. Well, let's just do an example. Suppose you measured at time t equals 0 that there were 7 cubic meters per second flowing. So that's you measured where the dial was on the gauge. At t equals 5, you got 10 cubic meters per second. At t equals 10, you got 4 cubic meters per second. What is the total flow between t equals 0 and t equals 10? Well, unless you measured somehow continuously all the time from 0 to 10, we don't actually know exactly how much the what the volume of water is, because between 0 and 5 there could have been a wild fluctuation in the flow rate here, and the same between 5 and 10. By actually just measuring at the individual points, we are forced to actually have an approximation, but we can use reasonable methods to get good approximations. If we could actually get the exact value for the flow, we would write it in this way, and this is the notation for a definite integral. We have an extended sign here like a long S. We write t equals 0, the beginning, at the bottom, t equals 10, the end, at the top, f of t, the flow rate that we're actually going to integrate, and dt here tells us what is the name of the variable. T is the name of the variable that we're going to use to describe our situation. From the individual measurements, we can only make an approximation to the value of that integral. The integral itself is always the exact flow of that we would get by a perfect approximation. So we can ask, how shall we do that approximation, and how shall we make the approximation better? Okay. Here I've plotted the 3 data points that we got in our sample. We have 7, 10, and 4. And I want to walk through 2 different scenarios. The first scenario is that we use the average value over the whole 10 seconds. So we take 7 plus 10 plus 4, divide by 3, and we treat that as the average flow rate, and what we're going to suppose is that's a good approximation to what happened during those 10 seconds. And we suppose that's what happens in each second, multiply by 10 seconds, and that gives us a total flow of 70 cubic meters. That's an approximate value, and it's an approximate value that we get by averaging all the flow rates. Now, it would be better, perhaps, if we took the average flow on the first interval and then the average flow on the second interval and calculated the flow during the first 5 seconds separately from the flow in the second 5 seconds. And that's what I've done here. The average flow in the first 5 seconds is 7 plus 10 over 2, 8.5. And the average flow in the second 5 seconds is 10 plus 4 over 2. Which is 7 cubic meters per second. what we see is that by doing this calculation, that the average flow rate was higher during the first 5 seconds than it was in the second 5 seconds. And so by doing this more detailed calculation, we're probably going to get a more accurate picture. And when we do the arithmetic, we take the averages multiplied by the length of the intervals, we get 7.7.3 cubic meters. So we get a different number. In fact, it's 10% different from what we got by just doing the straight average. This second method is what's called the trapezoidal method, and it gives a better approximation as we shorten the intervals for the measurement. Where do the trapezoids come from? Well, let's look at this picture. Here I have the same 3 red data points, but I've joined them by straight lines. Drop this line from the middle point down to 5, and what I have here are 2 trapezoids. A trapezoid is a geometric figure, a quadrilateral with 2 adjacent right angles. So it has these 2 parallel sides and a base. And the area of that trapezoid is the average of the 2 sides, the 2 parallel sides, multiplied by the base. So that gives us the area underneath that straight line. So what the trapezoidal method is actually doing is replacing the curve that we don't know by using the data points that we do know and joining them with straight lines. So it's a straight line approximation to the unknown flow. When we do the arithmetic, we get average of the first 2 times 5, average of the second 2 times 5 is 77.3 cubic meters. And that's the sum of the areas of the 2 trapezoids. And that illustrates our understanding of an integral as the area under a curve. Here's a different data set. Here I've taken an interval of only 0.5 seconds, and I have flow rates of 3, 4.2, 3, 5, 4, and so on. When we plot these, we get this blue curve, which I've drawn in as a straight line approximation. All I actually know are the data points that I've measured. And one approach to approximating the curve is to use straight lines as your approximation. If you take a numerical methods course, you will actually encounter various other ways you can approximate an unknown curve from some of its data points. But for this course, we'll only talk about straight line approximations. So what is the arithmetic? Well, to calculate the approximate value for the integral for the total flow over that interval from 0 to 3, we take the first 2, 3 and 4.23, take their average and multiply by the interval length. And then we take the second 2, 4.23 plus 5, take the average flow rate on that interval and multiply by 0.5. Because all the intervals have the same length, we can just factor that length out. And that gives us this series of averages that we add up and multiply by 0.5, and we get 9.92 as the approximate value for the total flow during those 3 seconds. Well, suppose this black curve is actually what was going on. Suppose the data points were just taken off of that black curve. Well, up here, the straight line approximation is doing quite a good job of approximating the curve. When we get down here, it does a particularly poor job of approximating the curve. And we could fix this problem down here by making the intervals shorter. So if we were to decrease these intervals even to 1/2 of what they are, we would get a much more accurate following of the black curve. And that illustrates how you can, even if you don't know what the black curve is, you will probably be getting a better approximation if you take shorter intervals. And finally, let's look at this calculation for the trapezoidal method. We factor out the common interval length, and then we add up the averages of the pairs of consecutive readings. And so we have 3 over 2 plus 4.3 over 2. Let's just not use a common denominator. Then the next one is 4.23 over 2 plus 5 over 2. And you see we get 4.23 twice. We get 4.23, half of it, and half of it again at 4.23. If I add those together, I'll just have 4.23. I have 5 over 2 plus 5 over 2. That's just 5. So you can simplify this trapezoidal calculation by thinking of it as taking all of the data points except the first and last and adding up those data points that you calculate, that you've gathered, and then you just take half the first and half the last and multiply by the length of the interval. And that gives you a very simple, straightforward way to do a trapezoidal approximation to an integral. And finally, let's just summarize. The trapezoidal method gives an approximation for the integral for the total flow. The trapezoidal method uses a straight line approximation of the curve. This is a numerical technique. It gives a number, so when you're doing numerical integration, your answer is actually a number. Using more and shorter measurement intervals gives better estimates usually. And in fact, if you take a numerical methods course, you will prove various results about how you can predict that your approximations will be getting better. And many modeling situations can only be analyzed by numerical methods. Even though your course will probably devote many weeks to finding antiderivatives, most of the models that are built can only be analyzed numerically. So it's an important technique to be aware of.